So let's work a few examples of estimating population means with confidence intervals. As I doubt you'll ever encounter the problem of estimating a population mean when the population standard deviation is known, we'll focus our attention on solving problems where we estimate the standard deviation from a sample and use a t-distribution. So let's talk about the first example. Let's say we're interested in measuring the shear strength of pre-stressed concrete beams. That is, we want to make a statement about mean shear strength by taking a sample of concrete beams. We'll collect a sample of 13 beams and measure the shear strength of each in kilonewtons. What is a 95% confidence interval for the mean shear strength of the population of concrete beams? So we have this data set in Excel, and we're going to take advantage of some Excel functions to help us find first the point estimate for the sample mean and also for the standard deviation. So if we use the average function in Excel, okay, so it equals average of our data range, okay, that will provide us with the sample average, the sample mean, okay? And also in Excel, we can use the stdev function for our range of observations to find the standard deviation, okay? So now what I always like to do whenever I solve these problems is to enumerate all the things I know about the problem first. Okay, so one thing I know is we want a 95% confidence interval. That means that alpha is 0.05. Okay, that is the significance level is 0.05. That would give us a 1 minus alpha times 100% confidence interval. Okay, so if we put 0.05 in, we get a 95% confidence interval. And as a result of this average function in Excel, we found that y bar, our sample mean, was 676.85 kilonewtons. Okay? And from the stdev function in Excel, we found that the sample standard deviation was 168.85 kilonewtons. Okay? Something else that we know is that the sample size n is 13. We had 13 different concrete beams that we measured the shear strength of. That means that our degrees of freedom here, because we're going to have to use a t-distribution, our degrees of freedom is 13 minus 1, or 12. 12 degrees of freedom. Okay? So now we want to implement the equation for the confidence interval for a population mean whenever we're using s in place of sigma. Okay? And that equation is y bar plus and minus t for particular degrees of freedom, alpha over 2 in the tail, times s over root n. Okay? So we have a point estimate plus and minus a margin of error. And remember, the margin of error is a function of variability, sample size, and confidence. Okay? Confidence, again, is represented with this alpha over 2 value. So we can plug in what we know from up here. One other thing that we need to figure out is what is our value of t. Okay, so we have to go to the t distribution, the t lookup table, and find for degrees of freedom 12 what alpha over 2, 0.05 over 2, pardon me, 0.05 over 2, so that's 0.025 in each tail. We need to figure out what this is from our t lookup table. So we go to the row 12, degrees of freedom 12. We go over to the column with 0.025 in the upper tail, and we find that that value is 2.179. 2.179. So now we've got everything that we need to calculate this confidence interval. We've got y bar, that's 676.85. We add to that and subtract from that t, 2.179 times s, which we have here, 168.85 divided by root n, root 13. Okay? And this is just arithmetic. This is very straightforward to do from here. If we work this out, we should get a lower bound of 574.81 and an upper bound of 778.89 kilonewtons. Okay? So what this says is that based on our sample of 13 concrete beams and the shear strength test that we did on those 13 concrete beams, we're 95% confident that the true population mean shear strength for the population of concrete beams lies between 574.81 and 778.89 kilonewtons. Okay? And we're 95% confident that the mean lies somewhere in there.